Okay, so today we're going to talk about proportionality and linearity. So we're learning about three kinds of relationships that ordered pairs, sets of ordered pairs called functions can have, and these relationships, they can be proportional, they can be linear but not proportional, or they can be neither linear nor proportional. Remember, everything that is proportional is also linear by definition or by proof, but we are going to separate those that are linear but not proportional into a second category, and we're going to learn how to identify all three types of relationships in this video. I'll have one example of a proportional relationship, three examples of linear relationships, and then one example of one that is neither linear nor proportional. And hopefully at the end of this video, everything will be crystal clear that we've been going on over in class and talked about in this video. So without further ado, as we like to say, let's move into the lesson. So let's first of all talk about what we looked at in class, where we talked about proportionality and the proportionality test. And we're going to show you, we had two tests that we run, but we're going to show you the easiest way to do this today, to identify whether a relationship is proportional, and it should be hopefully very straightforward after this video. So let's look at a relationship here that is indeed proportional. We don't know that it is, but we are going to identify it as such. And so we're going to look at these numbers: 2, 9, 4, 18, and 7, 31.5. We picked that interesting number here so that you might not be able to see the pattern quite so easily, and we'll have to do some math to figure out our answer. So the way that you identify a proportional relationship is you can simply do this. You can simply divide y by x, and if that number is constant throughout all for all ordered pairs, then you have a proportional relationship. So let's just write that here. We're going to write 9 over 2, and we're just looking at the individual pairs. So we're not looking at the difference between x's and y's. We're just looking at the individual pairs of numbers. Then we'll look at 18 over 4, and then we're going to look at 31.5 over 7. Now, if we do this division, we get, and we can just pull out your calculator and go ahead and divide 9 by 2, and divide 18 divided by 4. And I can do those in my head, but let me do on the calculator. I'm going to type in 31.5. You can feel free to do this on your own calculator. 31.5 divided by 7, and that indeed also equals 4.5. So the idea is that if y divided by x is 4.5 in all cases, then that means that x times 4.5 is 9, right? That's simply, times 4.5 times 4.5, right? Because if y over x in all cases is equal to 4.5, then through cross multiplication, 4.5 times x and 1 times y, I can say that y is equal to 4.5 times 4.5 times, let me just make that really easy to read, 4.5 times x. In fact, that is our definition of proportionality, right? Can we multiply a constant by the input to yield the output? Remember, this is our input, and this is our output. Our y is our output. So 2 times 4.5 is 9, 4 times 4.5 is 18, 7 times 4.5 is 31.5. So we have identified this is our equation. And over here we have our table or our t-chart. t-chart because we have this is this and this make a T. This is kind of like a double t-chart, a three-column chart. So this is our easiest example. If y divided by x is always a constant, we know that everything is, we have a proportional relationship. We don't actually have to run, any more tests. We have identified a proportional relationship. Notice that it's also, you could notice that it's also linear, and if we'll run some linear tests here in a second, and if you came back and ran this same linearity test on this data, you'd find out that this is also a linear relationship. But a proportional relationship in some ways is actually a stronger statement because we know if it's proportional, it must be linear. And actually, as you'll see, the test is easier. Now, the last thing to notice is that the ordered pair 0, 0 must exist in the chart. Now, this is true because we know that if we plugged in a 0 for our input, so if we, to our chart, we also came over here and we put our x and our y, and we had the 0 for x, our input, and we put a 0 in here for x, we say 4.5 times 0 is indeed 0. So 0, 0 would exist in the chart if we filled it in here. Okay, so that's our proportionality test. Now let's go forward and let's look at our linearity test. Now, linear relationship is a little bit more complicated to identify, but it's extremely powerful. It's a concept that we don't talk about in 7th grade math, but we do talk about it in 8th grade math and in the algebra. We talk about linear relationships, and it's about somewhere between 25 and 33% of all of algebra deals with linear relationships between numbers. So let's look at a simple, hopefully what's a simple example of a linear relationship, and we'll figure out how to write the equation of this relationship, and we're going to learn how to identify using our finding our change in y by change in x to see if it's linear. So we're going to identify if this set of numbers is linear, and then if it is linear, we will identify how or what the equation of the line is. So let's start here. We're going to put a 0 and a 6, a 1 and a 9, and a 3 and a 15, and a 5 and a 21. Now we can immediately see if we look a little bit closer at this, we can see quickly that this cannot be a proportional relationship because 9 divided by 1, if we ran our test, 9 divided by 1 is 9, and 15 divided by 3 is equal to 5. And because these numbers are different, it cannot be proportional. So this is not proportional. Okay, so I just kind of ran the proportionality test quickly. Now, once you find two numbers that are not proportional, then you don't have to run the test on the others, because it has to be true that every single number divides to the same number or has the same quotient. And in this case, that's not true. So this is not a proportional relationship. So we're just going to go ahead and erase that, knowing that we've done enough work to identify that. So now now our next test is, if it's not proportional, we have to find out whether it is linear. And now the linearity test requires us to look at the difference between numbers, between ordered pairs. And so we remember how we do that. We're going to make a little kind of a chart, if you will, or some lines here, and we're going to find the difference, and that's called delta y. So we're going to find our delta y, and remember, delta is the number or the letter. This is a delta, this symbol like this, and it's delta in Greek letters, and that means the difference. Delta means difference. And you can run D and D. So we're looking at a subtraction. Whenever we talk about delta y, we talk about the change in y, or we talk about the delta or the difference. So the difference between 9 and 6 is +3. The difference between 15 and 9 is positive 6. The difference between 21 and 15 is positive 6. Okay. Over here on the other side, we're going to find our delta x. And I invite you to just stop the video for a second and see if you can find the deltas on your own, and then come back. Okay. So stop the video and see if you can find these deltas. Okay. All right. Now that we're going again, hopefully you figured out that the delta here between 1 and 0 is a positive 1. The difference between 1 and 3, 3 minus 1 is a positive 2. 1 plus 2 is 3. And to get from 3 to 5 is a positive 2. Now what we're looking for, we're not looking for the change, the y's divided by x's. We just need to find out whether the change in y divided by the change in x is constant. So let's see. So we have 3 examples. And remember, we have to include every point. So every point is included in the calculation. So we're good to go here. So we're going to look at delta y divided by delta x. So in the first case, our delta y divided by delta x is 3 over 1 equals 3. That's our first one. Our second one is 6 over 2. So 6 and a positive 6 over a positive 2 equals 3. And then our last one is 6 over 2. We get a positive 3. So because the change in y over the change in x is all constant, it's all the same. So an equal change between any 2 inputs in the chart always yields an equal change in the 2 correlated outputs. So every time I increase x by 1, I increase y by 3. If I increase x by 2, I increase it by 6. So imagine if I increased x by 3, you can imagine that I'd need to increase y by 9. So you can find out and actually just write into this chart very easily if you wanted to. You could say, well, if I had this was 8, this would have to be 30. So delta y and delta x still have the same ratio. Okay. So now let's identify the equation. So now that we know it's linear, we know it has to be in this form. So I can write over here, y is equal to something times x plus something else. Let me just fill that in here. So we got to fill in these 2 things, which are our m and our b. Our m is always this difference here, this delta difference. So that's a 3. So when x changes by 1, y changes by 3. And so we're going to fit this 3 in right here. And that kind of makes sense. So if I go, well, we'll get back to that in a second. So that's a 3. That's this number. Now the way that you find our b is you go and you find on your chart or on your table where you say b is, where does my input equal 0? Question mark. Well, my input is 0 right here. And so if my input is 0, my output is 6. So my 6 is my b. And that is the equation of my linear function. So let's look at that. If I put a 1 in for x, I should be able to use this equation over here to get out a 9. So let's see if I put 3 times 1 is my input. Remember, back over here, 1, and I should get a 9 out. So plus 6 equals 9. And that's 3 plus 6 equals 9. And that's true. And we can do that for all of our numbers. We can do it for this one, 5 and 20. We can do it for 5 and 21. So 3 times 5 plus 6 equals 21. 15 plus 6 equals 21. And that's true. So these are validations that my equation is accurate. I can even look at this number that I generated down here and see if that one's also true. does 3 times 8 plus 6 equal 30, right? 8 and 3. 8 for my x, 30 for my y. So does 24 plus 6 equal 30? Yes, it does. Okay, good. So now we've identified how we can convert. Now we know how to convert charts into equations after we identify that we have a linear equation. So the first step, do we have a linear equation? If it's true, then we can use this strategy here to create this linear equation. And it's really cool that the pattern will always work for this equation. So let's go and let's look at another example that starts to get a little bit trickier. And then we'll do one that's a little trickier and then one that's the trickiest. So let's write this equation up here, or this chart. X and Y. And I'm going to leave a few spaces at the top, and you're going to see why I do this in a second. So we're going to say 2, 5, 4, 9, and 5, 11. Now what I want you to do is I want you to use the same strategy we used before and find your delta y's and your delta x's. And I'll let you stop the video right now and find out what those are and identify whether we have, do we have, question mark, do we have a linear relationship? And maybe you also want to identify whether it's proportional or not. And you should be able to find out really quickly using a calculator that we don't have a proportional relationship. This is not proportional because our proportionality test will fail. So stop the video right now and take a chance to find the delta y and the delta x. Okay. Hopefully you took some time to do that. So our delta y's, I always like to do the y's first. Not sure why, but over here we have a +4, and over here we have a +2. Over here, between 4 and 2, we have a +2 and a +1. So now let's identify our delta y divided by delta x. Well, our first one is a 4 over a 2, and that equals 2. And then our other one is a 2 over a 1, and that equals a 2. So because our delta y over our delta x is consistent, it's a 2, we know it we have a linear. We have a linear relationship. Now the question is what is our y equals mx plus b? So I'm going to write that over here. Y equals mx plus b. And these are our two unknowns. We have to figure out what these are. Well, we know what our x has to be. Our delta, our m is our change in y over our change in x. Whenever x changes by 1, y changes by 2. Whenever x changes by 2, y changes by 4. So that is our 2. Now the question mark is b. What is b equal to? Well, b is what y is equal to when x is 0. But I don't have a 0 in my chart. But I can create one. So let's look at how I might do that. I might put a 1 here. And I might put figure out what is y equal. Well, if then we can just work backwards. And we know that our delta y over our delta x must be 2. So if going from 1 to 2 is adding 1, then going from whatever to 5 must be a change of 2. So this has to be a 3. Now just stop. If that was confusing, take a second to realize that this has to be the right relationship, because we've already identified a change of 1 means y changes by 2. If x changes by 2, y changes by 4. So the only numbers that could possibly fit here are 1 and 3. And see how the pattern works going down. So now I want you to take a second to see what if x is 0, what does y have to be? So why don't you pause the video and see if you can figure out what goes in this spot. Okay, now we're back. So if I know that this is a +1 over here, a +1 relationship, then I know this has to be a +2 relationship over here. Just like before, going back from 2 to 1, I had to go back 1. I had to go back 2 on the y. If I go back 1 on my x, I have to go back 2 on my y, and I get the answer 1. Now remember, the number that goes in this B column, or in this B spot here, is basically the value of y, the value of our output, when our input is 0. And so that is indeed a 1. So 2x plus 1. So let's see, now that we've built this linear equation, it has to be true for all the numbers in our table. So let's just pick out two numbers like 5 4 and 9 and 5 and 11 and see if it works. Does 2 times 4 plus 1, does that equal 9? And the answer is yes, because 8 plus 1 is equal to 9. Let's look at 5 and 11. Does 2 times 5 plus 1, does that equal 11? Does 10 plus 1 equal 11? And the answer is yes, it does. So this is indeed our linear equation. It is a linear equation. Feel free to go back over this example if you'd like and come to terms with how we get our M and how we get our B before going on to the next problem, which is probably which will be the most difficult. But if you get this next one, you really have a deep understanding of what we're doing here in our algebra class. So I'm going to change the numbers, and they're going to get a little bit harder. But if you get this one, and maybe you have to watch this one a couple times, but if you get this one, you are on track in math class. And you can come tell me that and brag to me and say, Mr. Lipscomb, I think I really got it. Okay. And remember, so we're okay with calculators. So if you want, don't get all hung up on dividing and doing long division with decimals and all that stuff. Just get out your calculator, and we're learning about linear equations. We're not bothering with trying to get all of our, our 5th grade math right. So what we're going to do here is we're going to, first of all, if you'd like to identify whether this is proportional or not, you can. But what you're going to find is that it is not proportional if you do your dividing your y's by x's. But your delta y's divided by your delta x's, you're going to find is consistent. So I'll give you a second to do this math here. Find your delta x, your delta y, put your delta y's here, and put your delta x's here. And then come back and we'll identify if we have a linear relationship or not. Okay, so hopefully you've now done that. You've taken the time to identify that this is a +2 and this is a +2. Over here we have +0.5 and +0.5. And so our delta y over our delta x in both cases is equal to 2 over 0.5, which is equal to 4. And because this is also a +2 over 0.5, this has to be also equal to 4. So our delta y over our delta x is 4. It's constant, so we have a linear relationship. And let's just, because relationship. And so remember what we're doing here. We're finding y equals mx plus b, and we know that our m is 4. And I'm not going to go over that again because we've done it in the last two examples where we know that this delta y over delta x always is our m. So all we're left to find is our b here. Now the problem with finding b is it's hard to count back and figure out what we want to know what our 0 line is. When x is equal to 0, what is y equal to? And let me just do a little bit of erasing here so I can help us find this example, or make it a little bit more clear. So here's what I want you to think about. And then I'm going to leave you for a second and then come back and answer the question. So if this, I want to find out what y is equal to when x is 0. So if x goes from 0 to 3.5, 0.35, I want to find out what my y must be equal to. What did I have to add here? Now remember that in all cases, my delta y over my delta x must be equal to 4, or 4 over 1. Okay, so pause the video and see if you can think about if my delta x is 3.5 and my delta y is equal to something, and I know that that's got to equal 4 over 1. Okay. And we're going to figure out what this number has to be. Okay, so now hopefully you're back and you figured out what number goes here and the way that you calculated it. Well, let's put, we don't know what our delta y is, so we're going to just leave that as delta y. We're going to say, well, our delta y over our delta x. Well, we know what our delta x is between 0 and 3.5. Well, that's 3.5. And that has to equal 4 over 1. So let's do, so now we know, remember our building blocks. One of those things that we've been working on over the last couple weeks was cross multiplying. So if we say 1 times delta y, well, that's delta y, is equal to 4 times 3.5. Well, some of us can do that in our head, but I'll let you just take out your calculator and say 4 times 3.5. Well, that's 14. Okay, so if delta y's got to be 14, then this has got to be plus 14. So our so think about it again. You can think about it this way. Our delta y over our delta x, 14 divided by 3.5 has got to be equal to 4. And that would be, if we plug the 14 back in over here, 14 by 3.5 has got to equal 4. So what number plus 14 equals 13? Well, now we have to go back to our 5th grade math. You can do it 2 ways. You can take out your calculator and say 13 minus 14 is -1. Or you can just do it in your head. So now we have calculated the number, our output, when x is 0. And so what is our b? Our b must be, indeed, b is equal to -1. So plus -1. So y is 4x plus -1, and more often that's written as y equals 4x minus 1. And we have found our linear equation. Now, you can then go back and we can test our numbers. We can just test 4 and 15, see if that works. Well, does y equals 4 times x in our input, 4 minus 1, well, does that equal 15? Does 16 minus 1 equal 15? Yes, it does. So that's true. So we know that this number works. We could go in and we could test this number too, 4.5 and 17. We can try these two to say, well, does our output, if our output's 17, does that equal 4 times 4.5 minus 1? Well, 4 times 4.5 is the same as 2 times 9. So 18 minus 1 equals 17. True. So we have found our linear equation for this t-chart, just starting with 3, 5, 4, and 4.5. We didn't even have our 0 line, but we knew that we could calculate it using this strategy. So maybe take some time and rewatch this portion of the video. We'll do some more of these in class, but I wanted to make sure that I have something that you could review over and over again, should you need to. These will be on the next test and on the next quiz. Now what I want to do is I want to take you to the final example, and this will be one where we have neither a linear nor a proportional relationship. And you'll say, well, let's just try it out. Let's see if it's linear and is it proportional? And we'll run both tests on it. So you can figure out, you can learn for yourself how to run both of these tests in succession, and we'll see actually that this is neither. So we're going to say, well, if it's proportional, we have to say, well, y over x is consistent for all three numbers. And this looks like a pattern, right? One squared is 1, 2 squared is 4, 3 squared is 9. Hey, maybe this is proportional or it's linear because I know this pattern. Well, let's try and run our proportional test. Well, does 1 divided by 1 is equal to 1? And then we'll try it on the second point, 4 divided by 2. Well, 4 divided by 2 is 2. So, because we don't get the same division, the same quotient when we divide our y by x, it cannot be proportional. So this is no. This is no. It is not proportional, not proportional. So now let's run our linear test. And let's go through and let's do our delta y and our delta x and see maybe this is linear. Well, our delta y here is +3. Our delta x here is +5. Sorry, our delta y is +3 and our delta y between point 2 and 3 is +5. Our change between point 1 and point 2 is +1 for our x, and between 2 and 3 it's +1. So let's see, our delta y over our delta x for our first point is 3 over 1. Well, that's equal to 3. I screwed up my numbers here. Let me put my numbers back in. 4. And my x goes here. Okay, and then my other one is 5 over 1. My delta 5 divided by 1, and that equals 5. Well, these are not the same. Not the same. So this is no. This is so because these are not the same. This is not linear. So we have an example of a relationship that is not proportional, not linear, and you should know how to identify that. Okay, so we are going to go back here to our, just come home. We're just going to come home for a second and say, hopefully this was helpful to you, and please don't hesitate to ask any questions. If you got that last linear problem where we used the 3.5, the 4, and the 4.5, and I didn't give you the 0 point, give yourself a pat on the back, because that's really the cream of the top of what we're learning here, and you really have a good grasp on linearity. So give yourself a round of applause if you got that. And if you just followed most of this discussion, you did pretty well as well. So we'll leave you there and talk to you. We'll see you in class.